So thank you very much for the opportunity to present our company and what FRENELL might be offered to the Chinese emerging market of renewable energy. So my name is Selig. I'm presenting FRENELL, which is a German company specialized in FRENELL collector technology. On the picture you can see the principle of FRENELL collectors. I think you might be familiar with the main characteristics of FRENELL, which is using flat mirrors instead of curved mirrors. It has a parabolic trough, the same principle of a linear focusing system. So there is also one absorber tube arranged above the primary reflector. In this case, the receiver system remains in a fixed position, so the receiver does not move. The only moving parts are the mirrors continuously tracking the sun. So knowing about the big opportunity in China and the ambitious program of 10 gigawatt, we hope that we can help and contribute to the success of this amazing program. However, we are very clear that we can only altogether succeed if every stakeholder in this market will be focusing on his own core competence. And this is why I am presenting here the areas of core competence of FRENELL. First of all, we are looking back on 11 years of history. So FRENELL is a result from Molten Solar continuing its business. It's the same management, it's the same technology, the same patents, just the transfer of companies. Again, we want to specialize on what we can invest. You see here the whole value chain, as already explained here this morning. Project development, starting on the left side, is a very important function for the overall success of the plant. We have experience in project development. We did that in Spain. However, it's not our core competence, and we are happy to see that there are so many developers having already done wonderful work. Some of them are already based on FRENELL collector technology, so that's why we are happy to rather start in a collaboration than doing our own work. But if it comes to core competence, then it's clearly in the field of manufacturing. So FRENELL collector field is based on many single units. Some of them are very high-tech in terms of optical performance. And that's why we have specialized on those. They have a mass production principle for primary reflector units. So the prefabrication of elements is our core competence. And of course, if it comes to the assembly of a solar field, there are a lot of things which can go wrong or can be done right, and that is why the assembly of the FRENELL collector solar field is also a core competence area of FRENELL. Then, of course, we have, in addition, the thermal storage. This is already something where we see more companies in the market having the capacity and the experience to build up thermal storage systems using molten salt. And of course, if it comes to steam turbine-based power plants, I think China has an amazing capacity of competent EPC companies having experience in steam turbine-based power plants, may it be nuclear or coal-fired power stations. So this part of the CSP plant is just the same as in any other conventional thermal power station. That's why we think there is a big opportunity for us to collaborate with experienced companies in that area. Then, of course, it is also important to attract investors into such a plant. The ownership. We have been, we are 15% shareholder of a power station in Spain. However, this is an area which we want to leave open for utilities or independent private power producers here in China. But we won't leave them alone with the power station once it is built. So the professional maintenance and operation of the plant is also key for a high average performance throughout the lifetime of such a plant, and especially in the maintenance and operation of the solar field. We have many special tools, and we are happy to offer those special tools and services in the framework of our O&M contract. And if it was required, we could even do the O&M services for the power station, which we also have done in Spain for our customers. Looking back, what we have done over the last 11 years, the first was to build a power station demonstrating the performance of the system we had developed before. So we were able to synchronize the first commercial scale power plant using our FRENELL collector technology in the year of 2009. It is based on 22,000 square meter upper 2 area, which has been produced by our mass production factory in Spain. The capacity is 1.4 megawatt, so it's very small, but sufficiently large to demonstrate all the technical parameters a larger plant to be followed would also have. So it has identical parameters to a bigger one. It is owned by Novatec. It serves since 2009 as an R&D platform for every development step of our technology. It might be good to do some engineering and improvement on a computer simulation framework, but it's always important to test then the new ideas in the field, and then to potentially change and calibrate the theoretical model based on the experience and measured data taken from such a plant. That is why it's very important to have such a plant. We, as I already mentioned, were the manufacturers of the solar field. We have done the EPC for the entire power station, and of course Novatec is the owner of the plant. That was then an important first step, which created confidence to build a larger plant, which you can see here. This is now a 30 megawatt power station, using the same technology as successfully demonstrated at PE1. So it was finished in 2012. So we are looking back now on 4 years operational experience of that plant with 300,000 square meters and 30 megawatts. Key features of this system are that we are not using thermal oil as a heat transfer fluid inside the solar field. The benefit of a fixed receiver system is that it is capital to be operated with water and steam. So the steam every turbine needs to produce electricity is generated directly in the solar field. And that was an important feature to reduce costs. So we can mitigate the cost for the oil, we can mitigate the cost for exchanger transferring from the oil to the water steam circuit of a steam turbine. And we also mitigate the temperature limits of thermal oil. So thermal oil is only good for up to 390 degrees C. Of course, steam can be heated up on much higher temperature levels. This is another advantage of such a direct steam generating technology. The only disadvantage such a system has is that steam itself cannot be stored. It has a low density, it has a high pressure, therefore storage would be very expensive, and that's why it would be not the right technology for the Chinese market at the moment. Again, maybe something about innovation in CSP and how to transfer new ideas into a commercial product. This is a very long journey you need. You know that a CSP plant has a very high investment. There's a lot of money going into such a plant, and that's why it has to be very sure that this money will be successfully applied. And of course you can imagine that such a due diligence process will take quite some time. You can see here the structure of that project of PE2, and we are quite proud that even with the first customer project, we were able to attract utilities to become owner of that plant. Utilities usually are very conservative if it is about technical risk. It requires a long time to get them in. And so that's why we are very happy to have already 5 utilities sharing the ownership of that PE2 station. They are all coming from Switzerland. It was their first investment into new CSP technology, the first investment outside Switzerland. So therefore you can imagine that they did a very thorough due diligence. Of course they seek support from professional advisors such as Fichtner, and Fichtner carried out technical due diligence on PE1, and based on positive results they recommended to invest into the PE2 plant. Of course the utilities wanted not to invest on 100% equity, they wanted to have banks lending money, giving loans to the company, to the special purpose company, and this was another success that even in 2009, right after Lehman Brothers crisis, 3 commercial banks were prepared to provide debt to that special purpose company. And of course for us it was a great success to be the EPC contractor for such a first of its kind power station to be built. And we supported the customers with a 5-year O&M contract running the plant on a day-by-day basis for the first 5 years. Of course, the completion of such a plant depends on a performance test. In such a contract, we had to offer performance guarantees, ensuring the efficiency chain from solar radiation to net electricity output. So it is about the conversion from solar to thermal energy, from thermal energy to cross electricity. Then of course you have to deduct from this auxiliary power consumption for all motors, fans, etc. And then you come to the net electricity, which is then available to be fed into the grid. And this is exactly the value determining factor of such a plant. And we had to demonstrate over 3 different seasons that the performance guaranteed in the contract will be met under the prevailing weather conditions. And here you can see such a result. This was the summer test. You see that the blue columns, and they show the target net electrical output per day. So we had a computer model. This computer model was fed with the solar data and the ambient temperature, and then it calculated per 10-minute time step the net electricity output. And this was then accumulated over a day, and then the red column is the actual, the achieved net electricity. What you can see, that model and theory is slightly different sometimes, but overall you can see that we always were able to meet the performance. So, and that was then exactly what we achieved at the end, to be above the contractually agreed performance values, and that was then the reason for the owner to release the EPC contract and hand over the plant from us to them. There was another project we executed, this was in Australia at the same time, so in 2012 we were able to win in a competitive bidding process a contract where a solar field should integrate thermal energy, solar thermal energy into an existing coal-fired power station. That was quite interesting because CSP is not only interesting for new power stations, it is also an option to reduce the carbon emissions, the carbon footprint of an existing power station. And that's why we were very happy to win this contract, which we successfully completed also in 2012. However, all of those projects were based on direct steam, and again, I already mentioned, steam cannot be stored, and we think that CSP has only a chance in a market compared to photovoltaic if it makes a difference. And the difference between CSP and PV must be that CSP is able to produce electricity around the clock whenever there is a demand and not when only the sun is shining. And wind and photovoltaic will challenge the grid, so they just bring in electricity whenever the source is available, but they will leave more and more gaps to be closed by power stations capable to deliver power on demand. And that's why we realized this is really the chance for CSP, and this is why we started in 2012 a program to replace inside the solar field the heat transfer fluid. So we took out water and steam, and we said, okay, let's use the storage medium, which is molten salt in a CSP, and put that directly through the solar field, so that we could somehow then heat the molten salt in the solar field up to 550 degrees C. The molten salt can then be stored over daytime and is available for power production whenever power is needed. So that was the idea which we started with, again on PE1. When we started to communicate this concept with investors, with EPC contractors, the main question of everyone was, sounds very good, but what happens if you had to repair, for example, a receiver with the molten salt? How can you ensure that you can somehow empty the solar field in order you had, in the case you had to replace a vacuum tube? So therefore we said, okay, let's show how that works, and we did that. We successfully demonstrated more than 20 times how to empty such a solar field loop in order to carry out maintenance purposes. That is something which we have already demonstrated, a very important feature for maintenance purposes over 25 years lifetime. And another important question then was, okay, but what happens if you have a blackout, there is no power anymore, and the recirculation pumps stop, and you have no sunshine, and after a couple of times the molten salt gets frozen inside the solar field? Would you have to replace the entire receiver system? Would it be damaged? This was the main concern. And we took that very serious and said, okay, let's test how the solar field behaves and what we could do in such an unlikely event, unlikely situation. And that's what we did. We pumped, we circulated molten salt, we stopped circulation, we stopped focusing, and after 10 hours the molten salt was completely frozen inside the solar field. And with the special technology we have, we were able to demonstrate that after 6 hours we were able to remelt it and bring it back into operation. So this is a very important capability we have. This took quite some time, but this is really then, this has addressed the last question all the investors had, and whoever is interested could come and see the results, and we can repeat those tests. And this is why we feel now prepared for commercial scale applications. So we have done over 3 years all the tests necessary, and it takes some time to be prepared now for the market. Of course, we also showed, which was less challenging, that we can heat up the molten salt up to 550 degrees C. And this is another benefit. So if you have solar thermal energy, not on 390 degrees C, but on 550 degrees C, we can turn about 30% more of the thermal energy into electricity. You have just a more efficient steam turbine on such parameters than on a lower temperature profile. Another reason to significantly reduce cost of electricity. So this is what we have demonstrated, and another beautiness about FRENELL systems are that they do not have a single point of failure risk. So if you have a tower, you have one receiver and many reflectors. If your one receiver fails, the entire power station is shut down. And in a FRENELL system, you have always a fixed relation between primary reflectors and receiver units. And you have seen that we have already one loop successfully demonstrated at PE1. And if you then consider what is then the scale-up risk from what we have to a commercial scale project, then it is just the number of the same identical loops we already successfully tested. It is just more of the same, which makes the scale-up risk very low. And there's another advantage having such a technology. If you had a defect in one of the loops, it does not affect the entire power station operation. A big power station might have 100 loops, so if one loop had to be repaired, it's just an unavailability of 1%. And 99%, you can continue to operate the plant on a 99% availability factor. That's another important feature to increase the value of such a plant over its lifetime. So that's why we really think we are now prepared. And of course, we thought that's all good, but is it good enough to provide a cost advantage for the Chinese market? We would not come, so we were not convinced that we can somehow help to reduce the cost of electricity. We admire China's ambition to turn away from fossil-based power production to renewables, but of course, such a big nation cannot afford that it's too expensive. So therefore, we wanted to see to which levels can we get. And we did an exercise on a 100 megawatt scale, which you can see here. So we are very confident about the cost structure of the solar fleet. We have done it many times. We have, fortunately, many Chinese suppliers for key components. And if we consider the existing supply chain, still with a significant European and American content, then we can already show that the levelized cost of electricity could be in the range of 0.8 renminbi per kilowatt hour. So this is below the feed-in tariff of the first round. So therefore, we could provide an advantage for our customers selecting our technology for the first round, 1 gigawatt round. But of course, we are very confident to further reduce costs, to bring over time, by increase of scale, the cost of electricity coming from our FRENELL systems into the range of fossil fuel-based power generation. Also in China, where the direct solar radiation is not the highest. So in summary, we think we have done our homework. Again, we are very aware of what we can do and what we cannot do. So our business concept is based on collaboration, which I already outlined at the beginning. We think that the mass production technology we have for primary reflector is something which China does not have. We see a lot of capacity in the vacuum tube, but not so much mass production capacity in the primary reflector units, ensuring that those optical systems can be produced at high quantities and high quality, both together. So therefore, we think this is something we would be happy to bring into the country. And again, just looking backwards, we would be very proud to join this effort. And if we remember what happened in photovoltaic, it has been Germany starting with photovoltaic, and then it was China somehow rolling it out on a larger scale, and both countries together contributed greatly to the benefit of the entire global world to reduce the cost of photovoltaic. And we are really keen to showcase a similar success of the industries of both countries, Germany and China, hopefully to have the same success in the CSP. And that's why we are looking forward to a collaboration, hopefully very soon with you here in China. Thank you very much.
感谢马景先生分享。下面有人要提问吗？工作人员送一下话筒。
非常感谢这个马婷的这个报告。我有
稍等一下。
对，感谢马婷的报告。我有一个问题啊，就是说，从原来的这个 Molten 的水体系变成了我们现在FRENELL的这么一个熔岩体系，我们的基于考量点是什么？是因为刚刚我们所提到的水的这个蒸汽的储热的问题，还是有其他的这个技术风险，或者是有技术壁垒？这是我的问题。
Yes, so we did not test FE1 molten salt-based storage systems. But we did not think that there's a need to do so, because if you look at all the CSP plants in the world, more than 50% have already storage, and this storage is using already molten salts. So there are a lot of successful plants having molten salt-based storage systems. The only missing link, what they don't have, is that they heat up the molten salt directly in the solar field. So this is the new part. So, and this is exactly what we demonstrated. So therefore, we have now a proof that molten salt can be heated up in a solar field. And the proof that molten salt can be used in the thermal storage system can be found in many other CSP systems. So therefore, it was a lean approach. We only focused to demonstrate what is not already shown in the market. And if you combine both, of course it requires some good engineering to put everything together, but if you combine that with good engineering practice, it should be not a problem to design a fully functional molten salt-based plant. I hope this answers your question.
我的补充一句，就是那个水体，就是那个FRENELL的水体系的话，在您看来还有没有其他的一些问题？
Can you repeat the translation, please?
I understand. Please question.
This is just an interruption, so I don't get it.
Mr. Martin, he asked,
Yeah?
He asked about, do you think, is there any difficulty about the DSG technology still?
About?
DSG, the direct steam.
No, we have successfully demonstrated direct steam generation. So it is more challenging than molten salt, but it can be handled. It's possible. We have shown it. However, handling with heat transfer fluid, which is compressible, which changes its density and its volume, and which has a phase change, introduces high dynamic in the solar field. This is a big challenge. It can be managed. We have shown it. But we are very happy with molten salt. Having molten salt inside the solar field is much easier in terms of engineering challenges. So therefore, yes, DSG can work from an engineering technical point of view, but from a commercial point of view, economical point of view, since it does not allow storage, the plant capacity factor would be always limited to 20%. That means that the power block stands idle for 80% of the time, and that makes CSP power stations without storage very expensive. Therefore, from an economical point of view, we think direct steam generation will not have a future. Maybe in process heat, yes, but not in power generation. Power plants have to run either on base load to be cheap, to produce cheap power, and that is only possible with molten salt.
时间关系，我们就不再提问了。然后下面有什么问题的话，可以再和他沟通一下。范姐可能还有一个问题，再给范姐一个机会。
谢谢啊 ，Thanks Martin。我想问一个问题，就是刚才说你们在这个工况里面就有一个工况是说，在没有办法排空结热管就冻住的这种极端的情况下，可以来重新的这个融化能源和启动系统。我想问一下，这大概是在一个什么样的情况下？就比如说是这个管道就是非常影响流动性，还是说这个管道就是有部分冻结的这样的情况？所以就是这是一个在有多极端的一个工况。
I'm still waiting for the translation.
Okay, so I will ask you the question in English. You have just mentioned that you have some these control systems that if the pipe is frozen with the molten salt, and it could remelt the salt. So I would like to ask, what kind of risk is this you can evaluate? Is that the situation the pipe is full of the molten salt, or is part filled with the molten salt? Which is it a very risk situation or?
You mean how?
Extreme.
If it's frozen, what is the technique to melt it up?
I'm not asking technical. I'm just asking what kind of situation can you describe?
Yeah. So the regular operation of a molten salt-based power plant is that we continuously circulate molten salt. of course, when the sun is shining, to collect the heat and to put it into the storage. But if we have no solar radiation, we continue a minimum mass flow to compensate the heat losses. So we put then in molten salts at 220 degrees C, and it will lose its temperature to the outlet of the solar feed to 180 degrees C. So this is just to keep it liquid. We have to compensate the heat losses during night time. So, and this thermal energy will be taken from the thermal energy storage. Just for your information, the night losses through this operation are about 1% of the collected thermal energy over the year. So it's not very much we need, but what we need is, of course, a continuous circulation. We would have redundant circulation pumps, but if, for example, both pumps would fail because of a technical error, or that we would not have a power supply, we would have an interruption of power supply, uninterrupted power supply system would fail. This is all very unlikely, but if that happens, then it is about 5 to 10 hours time until it freezes. If then the operator does not drain the molten salt from the system, then only then we would have a freezing event. So it's very unlikely, but of course it is a risk. Yeah? And in that event, we would then have to apply our knowledge how to melt it up again for day-by-day operation.
Thank you.
看来大家对这个熔岩飞电这个技术还是非常的关注啊。那么下边的更多的时间，希望大家更多的和马挺先生多多的交流。再次感谢马挺先生。